The timeline of cement. Cement and concrete are the most widely used man-made materials in the world. They're everywhere. They're used to build our homes, our workplaces, and even statues in the park. They've survived through the Middle Ages and the Industrial Era, and they still reign today as the #1 building material. But what is concrete really? How is it made, and what makes it so useful? First of all, cement and concrete are often used interchangeably, but cement is an ingredient of concrete. Concrete is made up of cement, aggregates, and water, and cement acts as the glue that keeps it all together. Let's take a closer look into the timeline of cement production, starting with raw materials. The first ingredient to obtain is limestone. Limestone is mined as it comprises about 15% of the Earth's sedimentary crust. Other raw materials include silica sand, shale, clay, slate, and others which can be mixed in at various ratios to obtain different qualities. This mixture of raw materials is ground to produce raw meal, and then they are heated in a kiln to sintering temperatures which can go up to 1,450 degrees Celsius. During this step, three important things occur. Number one, calcium carbonate decomposes into lime, forming CO2. And this lime then reacts with other available materials to produce silicates, aluminates, and ferrites. This material is then ground to form something that we call clinker. Portland cement clinker is composed primarily of alite, belite, tricalcium aluminate, and tetracalcium aluminoferrite. Sometimes you may also have other materials including quicklime, wollastonite, yeelemonite, and periclase. Clinker is then ground in a ball mill with gypsum and other additives to obtain different attributes depending on the application. Gypsum is a common additive to control the setting time of cement. Additionally, supplementary cementitious materials may be added at this step to decrease the amount of CO2 emissions in cement and to modify the properties if desired. But this is only the first step of cement production. After the clinker is prepared and characterized and other materials are added, water is added to the mixture to start the dissolution process. After mixing, the molecules on the surface of the clinker grains are dissolved into the water, causing an intensive short release of heat. The small grains are completely dissolved, while parts of the larger grains remain undissolved or solid. As a result of the dissolution of these ions from the clinker, the pore solution changes its chemistry and it becomes more basic. The two main products of the hydration reaction are CSH and portlandite, but other hydrates can form during this step. Portlandite is crystal with a hexagonal shape, and it precipitates and grows in the pore space. The CSH, however, grows typically on the surface first of the clinker grains. Each of the phases of Portland cement react with water to give solid products which form the structure of Portland cement paste. In the beginning of hydration, primary portlandite, represented by yellow, crystallizes at numerous centers within the water-filled space. Other hydration products like CSH form in and on the grains. As hydration proceeds, the unhydrated grains become surrounded by thick rims of inner hydration product, and eventually this inner grain may become consumed. The hydration products are what cause the strength in cement to form, and over long periods of time, this compressive strength increases. Many parameters can affect the strength of cement, including the water to cement ratio, the size of the cement grains, and also the type of cement. On a smaller scale, we can see certain flaws by characterizing the boundaries between the various microstructural features. In particular, flaws can form on the boundaries between unhydrated grains and hydrates, inner and outer hydrates, and columnar zones. But really, any grain boundary is a great spot to form flaws. This takes us to concrete durability. For reinforced concrete, chloride ingress is one of the biggest threats for structure durability. It is, in fact, the most common reason for steel to corrode. When exposed to moisture or an exterior chloride source, chloride ions infiltrate concrete structures and transport within until they reach the steel-made rebars and corrode them. The high pH environment of cement paste, usually above 12.5, provides steel reinforcements with a protective layer. This naturally formed thin layer protects steel from aggressions which usually take form in destructive chemical reactions with harmful ions such as chloride. In the specific case of chloride ingress, the protective oxide film integrity of the reinforcements is controlled by two processes in competition: the repair or stabilization of the film by hydroxide ions, and the film destruction by chloride ions, which is also called depassivation. Depassivation of the reinforcing steel occurs when a sufficiently high chloride ion concentration is present on the steel surface. Sulfates can also be harmful agents that deteriorate concrete's lifespan. Unlike chloride, they attack concrete by reacting with hydrated compounds in the hardened cement paste. These reactions can induce sufficient pressure to slowly cause disintegration of the concrete. Alkali-silica reaction, or ASR, is an expansive reaction between certain forms of silica in aggregates and potassium and sodium alkalis in cement paste. It is basically a mineral acid-base reaction between sodium hydroxide, potassium hydroxide, or calcium hydroxide with reactive silica. The reaction results into the formation of silicate gel. However, the formed gel tends to swell and increase in volume once absorbing water. After reaching a certain point, the gel exerts an expansive pressure inside the siliceous aggregate, resulting in the loss of concrete strength and eventually leading to its failure. Indications of the presence of alkali aggregate reactivity may be a network of cracks, closed or spalling joints, or movement of portions of a structure. Carbonation of concrete is a process that is associated with the corrosion of steel reinforcement and with shrinkage. The term carbonation comes from the chemical reaction between carbon dioxide in the air and of hydration products in cement. The depth of penetration of carbonation depends on various different factors, including the porosity and pore solution system, which enclose all characteristics such as permeability, density, and porosity of the concrete, then the relative humidity, which directly influences calcium hydroxide dissolution, and finally, the CO2 concentration. One of the most popular ways to test for carbonation and measure the affected depth is by the use of the phenolphthalein indicator solution. The phenolphthalein indicator solution is applied to a fresh fracture surface of concrete. If the indicator turns purple, the pH is above 8.6. Where the solution remains colorless, the pH of the concrete is below 8.6, suggesting carbonation. So in conclusion, we started off with the mining of raw materials and the formation of clinker. We then looked a bit into the hydration process as clinker is dissolved and then strength begins to develop. We then ended our journey with a look at durability and ions that may affect the strength of concrete. Thank you for joining us on the timeline of cement and concrete. We would like to acknowledge and thank the EU Horizon 2020 Research and Innovation Program for making this research possible. We hope you have learned more about the timeline of cement, and please make sure to check out our other videos created by the entire ERICA team.